now we know what stereoisomers are and the idea of geometric versus optical, let's look at how we name stereoisomers, in particular the geometric isomers we were introduced to in our last video. So we looked at and we finished up with the idea of cyclic ring systems, where we can have the groups above or below the plane, so that if we have them on the same side of the ring, they're a cis isomer, and if we have them on opposing sides of the ring, they are the trans isomer. So in this case, we would have 1,2-dichloro cyclopropane. So this would be cis 1,2-dichloro-propane. And then this one here would be trans 1,2-dichloro-propane. So the cis telling us that the chloros are on the same side of the ring, trans telling us that the chloros are on the opposite side of the rings, however they are on the same carbon. Okay, so we get that again with 1,2-dichlorobutane. We have cis 1,2-dichlorobutane and trans 1,2-dichlorobutane. Ignore the methyl here. If it was methyl, we would have our ring here and we would have a CH3 group and a CH3 group. But again, we can have cis 1,2 and trans 1,2 dichlorobutanes as well. Dimethylbutanes. So when we name these, the two groups with the highest priority for naming are the same. So in this case, because we have butene dioic acid, so dioic telling us there's 2 carboxylic acids, ene telling us there's a double bond, and bute there's 4 carbons, so we have this 1, 2, 3, 4 carbon arrangement, 2 carboxylic acids. We are cis butene dioic acid or trans butene dioic acid. However, if the groups are different, we need to consider which are the highest priority to be able to identify which groups we would consider cis and trans to each other. Okay, so for example, 1-bromo-2-methyl-but-1-ene, we see we can have bromo, we have a methyl, and then we have this ethyl group here as well. So when we have conflicts of priority, we use a system known as E and Z isomers to name when we have different groups that are trans or cis across the double bond. Our rules for this are like this. So geometric isomers will occur in all alkenes. We can have cis and trans. We can only use cis and trans when they are simple, the groups are the same. Otherwise, we use E and Z. Z is the same as our cis. So one way of remembering this is if we just think cis, if we spell cis with a Z, cis is Z, and then trans E. Okay, so cis is Z, trans is E when we come to denoting them using the Z and E nomenclature. So when we look at rules for this, the first rule is look at the bond atom bonded to the carbon of the double bond. The atom with the higher atomic number has the higher priority. If they have the same atomic number, i.e. they're both carbon atoms, then you move out to the next atom. Okay, so longer hydrocarbon chains are going to have a higher priority. So a C2 chain is going to be a higher priority than a CH3, which will be a higher priority to an H. When we look at our halogens, bromine is going to be a higher priority to chlorine, which is going to be a higher priority to fluorine. We compare the positions of the highest priority groups. If they're on the same side, they're Z. If they're on the opposite sides, they're E. So if we look at the example we were looking at before, where we have the bromo, we have our methyl, and we have our ethyl, this means when we're comparing, we're going to look at the first carbon. We have bromo and hydrogen. Bromo has the highest priority, so we will be looking at it. And then when we come to the next carbon, we have a carbon and a carbon. So we move out to the next one, and the next one for this one will be another carbon versus a hydrogen. So our ethyl chain, our ethyl group here, will have the higher priority. So in this case, it would be a Z isomer because the bromo and the ethyl are on the same side of the group and they are our highest priority. Okay, so we end up with this configuration here would be Z, 1 bromo, 2 methyl but-1-ene. We still need to find our longest carbon chain. Okay, so we're still going to be going 1, 2, and then 3 and 4 for the 2 out here. So we have 1 bromo, 2 methyl, name it as we normally do, but-1-ene, but it is going to be the Z configuration. For the other one, if we change the position of the ethyl and the methyl groups, then we will see now we still have 1, 2, 3, 4 for our longest chain, but we will be 1 bromo, 2 methyl, but-1-ene as we were before, but this time we would put the E out the front as the E configuration of this isomer. So cis and Z refer to the 2 highest priority groups being on the same side. Cis is the same, Z is different. Okay, so, and if the Z, I like to think about the Z, we've got that transection line here, so to think that we're crossing sides, that helps me remember that our Z isomers are also our trans. So the highest priority groups being on opposite sides is trans. The highest priority groups being on the same sides is cis, so we have Z and E isomers. Just looking at physical properties and polarities of these, because we know that polarity strongly affects boiling point, we can see that if we have different polarities here, we can possibly change the polarity of the molecule. In this case, our dipoles are going to cancel out. If we think of vector addition, there'll be no net dipole on the trans isomer. Okay, so we will have no net dipole on the trans isomer. So in this case, this would be non-polar. However, on the cis isomer, we will actually end up with a net dipole where we would have one side that would be more negative than the other. So we would have a polar cis isomer. This means that our cis isomer would have the higher boiling point than the trans isomer. The trans isomer would only be held together by dispersion forces, whereas the cis isomer would have dipole-dipole interactions. And this is critical when we start thinking about evaluating different compounds in the way that we think they would behave. So when we are comparing the overall boiling points, it is important to make sure that you pay attention to which way your dipoles will be going. Are they going to cancel each other out, or are they going to add together? Same goes for shape. The symmetry or the shape of the molecule can interfere or enhance the way molecules can pack together, and we saw this with straight chain versus branched isomers. So trans isomers tend to be more symmetrical and will pack more efficiently. So this is our trans isomer here. So we can see that we have this sort of curving shape, so another one could sort of come in here. Whereas the cis isomers, we tend to put all the bulk on one side, so they tend to not pack together as well. So our cis isomers, due to steric effects or physical shape, will tend to have less packing, while trans isomers will pack together more efficiently, and this can affect our dispersion forces. This can also, if you think about it, affect our hydrogen bonding depending on the position and orientation of our hydrogen bonding groups. If we have a cis molecule that contains carboxylic acids, for example, we can have hydrogen bonds forming within the one molecule and then leaving only one position open for bonding to other molecules. Whereas if they were trans, these hydrogen bonds would not form within the molecule. We would have extensive intermolecular bonding, so we would have a higher boiling point here. Okay, we're going to have less interactions between molecules, lower boiling point, more interactions between molecules, so higher boiling points. So always consider what the groups will be doing and the size. When we talk about groups coming in together, if we have large bulky groups that might interfere with each other or overlap, we refer to this as steric hindrance. In the case of cis molecules, we can see steric hindrance where these methyl groups would interact with each other, and that would be more unstable than if we have the trans groups where the groups have plenty of room to move, remembering that these are still electron clouds and things like that, so we can have repulsion occurring. So we would tend to see the formation of the trans 2-butene isomer more than the cis 2-butene isomer because it is less stable, and less stability tends to mean less often occurring in the world of chemistry. Because of this, it also affects their reactivity. The spatial arrangement will affect whether or not groups are close enough or in proximity to each other enough in order to be able to react. Okay, so the spatial arrangement of functional groups leaves two different chemical properties. That's it for our geometric isomers and the way that we name them and the properties that we see. Next up, we'll have a closer look at chiral and then move on to SN1 and SN2 reaction mechanisms. See you in class.